Have you ever paused to truly consider the very fabric of our universe? I mean, really think about it.
Not just the stars and galaxies, the big stuff we see.
Exactly, but the invisible threads that seem to weave reality itself together. What if, everything we think we know about fundamental properties, things like mass or the spin of a tiny particle,
Or even gravity, the biggest force of all.
what if that's all just scratching the surface? What if there's a deeper, maybe more unified understanding emerging that could, well, redefine everything?
It's a profound thought, absolutely. And frankly, it's one that classical physics, even quantum physics, despite all their incredible successes, haven't completely nailed down.
Right.
Imagine if the familiar concepts we use, the language we use to describe the universe, are, in a way, just shadows.
Shadows.
Yeah, shadows cast by a far more fundamental and much more dynamic underlying reality.
That's precisely the fascinating frontier we're diving into today.
Yeah.
We're going to unpack some truly mind-bending concepts. They come from a groundbreaking theoretical paper published back in 2025 by Philip Randolph Lilien.
Ah, yes, Lilien's work. He introduces this revolutionary idea he calls hyperchirality.
Exactly, hyperchirality. And it's part of a much larger, really grand, unified theory he's developed, known as the HHHCR-TOE.
Quite the acronym.
It is, but it's a vision that genuinely challenges our conventional understanding of physics. It really makes you rethink things.
So our mission in this deep dive, really, is to give you a unique shortcut. We want to guide you through these incredibly complex ideas about how reality might actually be structured.
We'll try to distill the most important nuggets of knowledge, the key insights.
Right. Even if the physics sounds dense at first, and some of it is, our goal is to make these profound concepts accessible. Hopefully spark some of those aha moments.
Those are the best moments.
They really are. They make learning so rewarding.
Exactly. So we're going to help you unpack what hyperchirality truly means, why a whole new kind of geometry called Finsler geometry is apparently absolutely crucial for understanding it.
And how this all fits into a potential theory of everything. One that could redefine everything from the nature of mass to the enduring mystery of dark matter.
Get ready to rethink foundational physics. We're setting the stage for a journey really beyond simple notions of particles and into the very essence of something called coherence emergence.
Let's do it.
Okay, let's begin our deep dive then with part one. The HHCR-TOE, a universe woven from coherence.
Right, the big one.
The full name is the hypersymmetric, hyperfractal coherent resonance theory of everything.
Still a mouthful.
Definitely a mouthful. But conceptually, it's presented as this foundational theory. It models reality not as, discrete particles interacting, which is our usual framework.
A sort of billiard ball view almost.
Yeah, exactly, but as something more fluid. It's described as coherence emerging across nested dimensional manifolds. So if we're talking about reality being woven from coherence, what does coherence even mean in this incredibly broad, almost cosmic context? It's not just lasers, right?
That's a crucial first step, absolutely.
Yeah.
And no, it's definitely not just lasers. In the HHHCR-TOE, coherence is far more fundamental than our everyday understanding, like light waves being perfectly in sync.
Okay.
While quantum mechanics uses the term, sure, this theory takes it to a deeper, almost ontological level. You could say it's about the very nature of being.
Ontological, wow.
Yeah. Here, coherence refers to a fundamental dynamic field structure, what the paper calls a coherence tensor. Think of it as the ultimate state of order, maybe, where everything is perfectly aligned, perfectly resonated.
Like a perfect symmetry.
Exactly. This coherence tensor doesn't just describe light. It expresses local symmetry, directionality, and resonance phase stability across all scales. It's the deep-seated principle that governs the very emergence of everything we observe.
Everything like what?
Well, from mass and spin, which we'll definitely get into, to the chirality or the handedness of particles. It's almost as if the universe itself began as this pure, coherent song.
A song. I like that analogy.
And everything we see, every particle, every force, is just a note or a chord, a vibration from that original harmony.
So this theory suggests a universe where everything from the tiniest, seemingly indivisible particles to the largest gravitational effects we see across galaxies.
The whole range.
It all emerges from this deeper, unified coherence field. It's like reality isn't built from Lego bricks,
Right, not static blocks.
but rather from the harmonious interplay of these underlying waves or vibrations.
Precisely. And this framework offers a really radical departure from conventional physics. In our current standard model, we often view things like mass or spin as fundamental, right? Inherent properties of particles.
Yeah, an electron has spin, a proton has mass. It's just what they are.
But the HHHCR flips this perspective completely on its head. It views them not as intrinsic independent properties, but as emergent phenomena.
Emergent, meaning they arise from something else.
Exactly. They don't exist in isolation. They're a direct result of this underlying coherence field interacting with itself, bifurcating, splitting, essentially, and forming patterns.
So the paper actually says mass and spin emerge?
Explicitly, yes.
Yeah.
Concepts we take for granted, like mass and spin, are seen as something that emerges from this underlying coherence. It's a profound shift, moving from thinking about fundamental building blocks to thinking about fundamental patterns of vibration.
And to really understand the origin of these patterns, these vibrations, the paper introduces something called the omnilectic field. It's described as the very highest layer of this coherence.
Yeah, the ultimate source.
It sounds like the primordial canvas, maybe, the place everything else flows from.
That's an excellent way to put it. The omnilectic field is described as the highest, most undifferentiated coherence field layer within the HHHCR. Imagine just pure, unadulterated potential. Perfect symmetry, perfect coherence. From this ultimate field, all directional and asymmetric structures, all the complexities and differentiations we observe in our universe are said to emerge. It's the initial state of pure, omnidirectional coherence.
Omnidirectional, meaning no preferred direction at all.
Exactly. And from that state, complexity, individual particles, and ultimately our observed reality all arise. This concept really sets the stage for understanding how such incredible complexity in the universe could, theoretically, be traced back to a more fundamental, unified simplicity.
Like the ultimate source code for reality.
That's a great analogy. It's the base layer from which everything else is generated.
This all sounds incredibly ambitious. I mean, it really is a theory of everything. But it raises an important question. Why do we even need this new perspective? What are the limitations of our current understanding that this theory is trying to overcome?
That's a fair challenge, absolutely. The paper highlights that our conventional understandings of fundamental concepts, chirality, spin, even space-time itself, are often limited by what it calls space-time limited frames.
Space-time limited frames, what does that mean exactly?
It means our current physics models are incredibly good at describing what happens within space-time, how particles interact, how gravity behaves, the rules of the game as we see it.
Right, they work incredibly well for prediction.
They do. But they often struggle to explain how these properties truly come into being, or why space-time itself has the properties it does. They're descriptive, but maybe less generative.
Generative, meaning explaining the origin.
Precisely. This new framework, the HHHCR, aims to offer a generative rather than descriptive account of reality. It's not just about categorizing what's already there, but fundamentally explaining the process of how things differentiate, how they emerge from that deeper, more unified source of coherence.
So it's about the how and the why, not just the what.
Exactly. It's about the very act of becoming, rather than just describing the state of being. It seeks to answer why, not just what.
Okay, so it's like moving from a highly detailed description of a finished painting to understanding the entire process. How the artist chose the canvas, mixed the colors, the brush strokes, layered the paint, all of that to create the final image.
That's a fantastic analogy.
And to do that, you don't just need a bigger canvas, you might need a different kind of canvas altogether. Which brings us neatly to part 2, Finsler geometry, the dynamic canvas of reality.
The mathematical underpinning.
Right. This is where the mathematical language becomes absolutely crucial, because the paper suggests we need to go beyond our usual geometric tools, the ones we normally use, to describe this emerging reality.
Precisely. And to get our heads around Finsler geometry, let's start with what you might already know, or at least have heard of.
Okay.
If you've encountered Einstein's general relativity, you're familiar with Riemannian geometry.
Right. The math of curved spacetime.
Exactly. That's the math that describes how mass and energy warp the fabric of the universe. Now, in Riemannian geometry, if you're standing at a point, the stretchiness or the geometric properties of space are the same no matter which direction you move from that point. It's what we call isotropic, meaning uniform in all directions. Think of a perfectly smooth, evenly stretched rubber sheet. The curvature is the same whichever way you push off.
Okay, so a meter stick measures the same length, whether I point it north or east or up or down from a specific spot. That's Riemannian, or even just regular, flat, Euclidean geometry.
Correct.
But if I'm understanding this correctly, Finsler geometry is different. Imagine a space where the stretchiness or maybe the density of space actually changes depending on which way you're trying to move. Is that the idea?
That's a perfect way to visualize it. Finsler geometry is defined as a generalization of Riemannian geometry, where the metric, that's the mathematical tool for measuring distances and angles.
The ruler, basically.
Kind of, yeah. The metric depends on both your position, which we usually denote as x, and your correction of motion, let's call it y.
Position and direction.
Exactly. So unlike that standard grid where every step is uniform, in Finsler space, taking a step north might be fundamentally different, geometrically speaking, from taking a step east, even if you start from the exact same spot x.
Like walking through different terrains?
That's another good analogy. Imagine trying to walk across a tightly woven carpet versus trying to walk across a loose, shaggy rug. The effort, the effective distance, feels different depending on the direction of the weave. This directional dependence is absolutely crucial for capturing the anisotropic or direction-dependent phenomena that the HHHCR describes.
Anisotropic, meaning not the same in all directions.
Correct, which is the opposite of isotropic.
So why is this specific, more complex geometry so essential for coherence physics? Why can't we just use the Riemannian geometry we already know, which has worked so incredibly well for so long?
Well, this raises that important question. If reality emerges from coherence, and that coherence has inherent directional flows and asymmetries again, think of water flowing in currents, not just sitting still like a perfectly calm pond.
Right, it has a directionality.
How do we mathematically describe that in a way that truly captures its dynamic nature? Traditional geometry, like Riemannian, fundamentally presumes an isotropic metric, meaning geometry only depends on position, not direction. The paper explicitly states that this is insufficient for coherence physics.
Because coherence itself isn't isotropic.
Exactly, because coherence emergence is described as inherently anisotropic, meaning directional gradients aren't just present, they're crucial to how things form and evolve. Finsler geometry perfectly accommodates this anisotropic propagation, torsional curvature, and field asymmetry.
Torsional curvature, like twisting.
Yeah, twists and direction-dependent bends. Finsler geometry is the natural language to describe a universe where the underlying fabric has directional preferences, where its very grain can change depending on which way you're looking or moving.
And it sounds like the Finsler metric itself isn't just a static measurement tool like a fixed ruler. It's dynamic, described as almost a coherence modulator.
Yes, that's precisely the insight. The Finsler metric, denoted as fxy, acts as a modulator of local coherence density. Here, the direction y corresponds directly to the tangent vector of coherence flow, and x is the point where these resonance conditions are being evaluated.
So the metric itself encodes the flow.
It does. This allows us to integrate, mathematically speaking, not just along simple geometric paths, but along what the paper calls resonance trajectories.
Resonance trajectories.
These are specific paths in the manifold where coherence fields propagate, interact, and importantly, reduce anisotropically, meaning they lose some of their directional uniformity, their perfect symmetry, as they move.
They become less ordered.
In a sense, yes, or more structured in a specific direction. In essence, the Finsler metric quantifies how coherence densities evolve and bifurcate into asymmetric field structures. It's the mathematical engine describing how the universe generates its incredible complexity from its fundamental coherence, by allowing that coherence to flow and twist in specific, directionally preferred ways.
And this leads to a new understanding of the very fabric of reality as a manifold of coherence reduction. Which sounds like it's not just a passive stage for physics to play out on,
Not at all.
but an active participant in shaping reality. Right?
Absolutely. In the HHHCR the theory proposes something quite revolutionary, that dimensional structure itself arises via nested coherence reduction.
Dimensions arise. They aren't just there.
Not fundamentally, according to this. Our familiar three spatial dimensions plus time aren't just given, they emerge from something deeper. And Finsler geometry captures this by encoding the breakdown of isotropy, that loss of uniformity in all directions directly within the manifold's tangent structure, the y dependence.
Okay.
So the manifold isn't a passive arena where fields just evolve however they want. Instead, it's conceived as a coherent structured operator that actively modulates the dynamics of symmetry reduction and phase bifurcation. It intrinsically encodes anisotropy, not as some external force acting on space, but as a core dynamic property of the coherence field itself, sculpting the very dimensions we perceive.
That's truly mind-bending. And it ties into this idea mentioned in the paper, nested hyperdimensional layering. Does this imply our everyday 4D spacetime is just one projection or layer of something much larger, something maybe unfolded?
It does. That's exactly the implication.
Uh-huh.
Finsler geometry is perfectly compatible with this idea that our familiar 4D spacetime is simply one projection layer of a higher dimensional structure.
Like Plato's cave, almost.
In a way, yeah. In this context, the directional vectors y in the Finsler metric, the directional part, can contain components from hidden coherence layers.
Hidden layers.
Imagine a multidimensional tapestry, incredibly complex, and we're just seeing the intricate pattern of one thread projected onto a flat 4D surface. This means the Finsler metric can encode influences from these unfolded hyperfractal dimensions, even if these dimensions aren't directly observable in our everyday reality.
Hyperfractal, like fractals but in more dimensions.
Sort of, yeah, suggesting complex, self-similar structures across dimensional scales. It reinforces Finsler geometry's role as potentially a multi-layered tensor scaffold that can structure everything from the asymmetries we see in particle masses to the resonance patterns of particles.
All emerging from these deeper coherence differentials.
Exactly. It's a mathematical language for describing how our reality might be just one facet of a much grander, more complex, and incredibly directionally rich universe.
Wow. Okay, that brings us to part 3. Hyperchirality unpacked the signature of asymmetry. Now, when we talk about chirality in conventional physics, we often think of it pretty simply, right? A particle being left-handed or right-handed.
Like our hands, yeah. Mirror images, but not superimposable.
Exactly. It's associated with spin or parity transformations, and it's usually confined to spacetime.
That's the typical, well-understood view in the Standard Model. It's treated as a property assigned to a particle, often linked, for instance, to how it interacts with the weak nuclear force.
But here's where it gets really interesting, as you said earlier. Lilien's paper completely redefines chirality. It's not just about a particle having a handedness in spacetime.
No, it's much deeper than that.
Yeah.
It's about something far more fundamental, something embedded in the very fabric of the universe's coherence.
So hyperchirality isn't just a bigger, more complex version of regular chirality.
Not at all.
The paper redefines it not as some extension of spin, but as a fundamental operator of coherence asymmetry. That sounds important. An operator embedded in the tensorial structure of the coherence field, and it quantifies broken omnidirectionality. Okay, let's break that down. What does broken omnidirectionality mean, and why is that such a profound redefinition?
Okay, think of it this way. Imagine that perfectly pristine, ideal coherence field we talked about, completely uniform, perfectly symmetrical in all directions.
The onelectic field state.
Right. Omnidirectionality would be that perfect state. Hyperchirality, then, represents the precise measure of how that ideal coherence field deviates from perfect symmetry. It's how it becomes asymmetric, how it starts showing preferences or biases in certain directions.
Okay, so it's the degree of broken symmetry.
Exactly. And this asymmetry emerges through directional reductions in the coherence field itself. The paper calls it a resonance torsion operator, which implies it's dynamic. It's tied to twists or imbalances in the fundamental field flow.
So it's not a static label, like left-handed particle?
No, it's a dynamic, active process of symmetry breaking. It's the signature of the universe making a choice, so to speak, to differentiate in a particular direction.
Yeah.
It's the act of becoming asymmetric.
So instead of chirality being a fixed property of a particle, it's fundamentally a phase asymmetry operator of the underlying coherence field itself.
Exactly. Chirality is seen as the direct result of a phase bifurcation in the onelectic coherence field. Imagine that perfectly balanced coherent field, and then at some point it splits or bifurcates like a path splitting in two, becoming asymmetric in a specific direction.
And there's math for this. A tensor.
There is. The hyperchiral tensor, which the paper defines with a specific mathematical expression involving gradients of the coherence tensor. Well, conceptually, you can think of it as encoding the directional torsion of coherence, or, maybe more simply, a coherence flow imbalance.
And an imbalance in the flow.
Right. It's what produces what the paper calls spinor resonance splitting or tensor bifurcation. This means the appearance of left or right-handedness in particles is an intrinsic outcome of the field's dynamics, not some arbitrary assignment given to them.
That means chirality isn't something that's just assigned to a particle at its birth, but it's dynamically generated rather than statically assigned.
Precisely.
And you mentioned it's in the same fundamental category as curvature and torsion, which are properties of space-time itself, or the manifold. That's a huge elevation of its status compared to just being a particle property.
It is. This really highlights the geometrization of asymmetry. It ties chirality directly to the dynamic processes of the coherence field, putting it on par with the fundamental geometric properties of the manifold, rather than just being a label or an external property tacked onto a particle.
And this dynamic generation must be linked to the Finsler geometry.
Intricately linked, yes, because it's the Finsler manifold with its inherent directional sensitivity that provides the stage for these directional biases, these hyperchiral asymmetries, to manifest and be described mathematically.
Okay, speaking of the Finsler metric, how do hyperchirality and the Finsler metric tensor connect in practice? How does the math show this link?
Well, coherence asymmetry manifests when the Finsler metric deviates from symmetry in its directional components. Remember, Finsler geometry uniquely allows for direction-dependent measurements, fxy.
Right, the y part.
So if the metric behaves differently when you measure something in one direction, y, versus the exact opposite direction, that's a clear, quantifiable signature of hyperchirality. The paper introduces what it calls a hyperchiral distortion operator.
A distortion operator. What does it do?
It basically quantifies this non-invariance under directional inversion. Think of it as a specialized coherence resonance diagnostic, a mathematical tool capable of detecting the embedded hyperchiral structure, the inherent handedness of the manifold itself.
So it measures the difference between forwards and backwards, essentially.
In a geometric sense, yes.
Yeah.
And it generalizes the traditional notion of parity violation, the idea that some physical process is distinguished between left and right, like in the weak force, into a fundamental field-encoded anisotropy, meaning this directional preference is built right into the very fabric of the field, described by the Finsler metric.
So what does this all mean for the fundamental nature of reality, then? Does this hyperchirality ultimately represent a coherence bifurcation, a fundamental splitting?
It absolutely does. More fundamentally, hyperchirality is treated as the symmetry-breaking eigenmode of the coherence field itself.
Eigenmode, like a fundamental way of vibrating.
Exactly, like a natural resonance pattern within a system. When the coherence field undergoes a symmetry-breaking event along a specific direction, when it chooses a preferred pathway, losing its perfect omnidirectionality, that's what we call a hyperchiral bifurcation.
Okay.
This ties chirality directly to the eigenstructure of directional coherence modulation, the fundamental ways the field can become asymmetric. And this allows us, in principle, to predict spinor behavior and particle asymmetry from first principles, from the structure of the coherence field itself.
So it unifies a lot of concepts.
It really does. This deeper definition allows hyperchirality to unify the concepts of chirality, torsion, parity violation, and symmetry breaking under a single geometric ontological umbrella. It's a truly powerful unifying concept, suggesting a universe where fundamental properties are simply expressions of deeper dynamic symmetries breaking in specific directional ways.
Wow. So chirality is really about how the universe's fundamental coherence field twists and turns, generating asymmetry as it moves from perfect order to the structured complexity we observe.
So the great summary of it.
And this leads us directly to part 4. Spinors reimagined from algebraic objects to resonance bivectors. This is another area where the paper seems to directly challenge conventional wisdom in physics.
Indeed. It really goes after some foundational concepts. In traditional physics, spinors are usually described as algebraic objects representing states in complex vector spaces.
Math objects, basically.
Pretty much, yeah. They're mathematical entities used to encode chiral features through things called Lorentz groups, which describe the symmetries of space-time. In essence, they're the mathematical tools we use to describe particles with intrinsic angular momentum, with spin, like electrons.
But the paper challenges this view.
It does. It states that this conventional definition is insufficiently generative in coherence physics, meaning it describes spinors well, but it doesn't explain where they come from, their fundamental origin. It doesn't generate them from first principles.
So how does the HHHER toe redefine them? What are they, if not fundamental algebraic objects?
It's a radical redefinition, really. Instead of being fundamental algebraic entities, spinors are described as not ontologically primitive, but rather coherence-derived bivectors.
Bivectors. What's a bivector?
Okay, think of a vector as pointing in a direction, like an arrow. A bivector is more like something that describes an oriented plane or a fundamental twist or rotation in space, not just a point or a line.
Ah, okay. Like an area with a direction.
Kind of, yeah. And these spinor bivectors are described as localized expressions of symmetry reduction within the directional resonance lattice of the Finsler manifold.
So they appear when symmetry breaks locally.
Exactly. So the familiar spin we attribute to particles, that intrinsic angular momentum, isn't an inherent fundamental property in this view. Instead, it's merely a projection of a more fundamental resonance structure undergoing bifurcation across anisotropic coherence gradients.
So spin is just how we see this deeper structure.
Precisely. This means spin is a manifestation of something deeper, a consequence of the coherence field itself twisting or flowing in a localized, structured way. It's an emergent shadow, not the fundamental thing itself.
Okay, that's a lot to unpack. Could you help us visualize what these coherence bivectors are and how they lead to directional emergence, ultimately giving rise to what we perceive as spin?
Certainly. Let's try. A resonance bivector, which the paper denotes with a specific mathematical symbol, is conceptually defined as the antisymmetric component of coherence field fluctuation.
Antisymmetric, meaning it changes sign if you swap indices.
Right, which captures that rotational or twist-like quality. Imagine a perfectly smooth, coherent flow, like honey flowing evenly. Now picture a tiny disturbance, a localized eddy or swirl in that flow. This bivector captures that localized coherent circulation, or a quantized twist in the directional tensor flow.
A tiny whirlpool in the coherence.
The paper explicitly likens it to a vortex in the coherence field. That's a great image. When this bivector, this tiny vortex, is projected onto a lower dimensional subspace, like our everyday 4D spacetime,
The shadow again.
that's what appears as spin. So what we observe as a particle's intrinsic spin is actually the projection of the localized twist or circulation of the underlying higher dimensional coherence field. It's an emergent phenomena rooted in the field's dynamics, not an intrinsic property assigned to a point particle.
That's a fascinating way to think about it. And because we're operating within the unique framework of Finsler space with its directionality, it naturally leads to Finsler covariant spinor fields and dynamic gamma structures. How does that come into play? How does the geometry affect these spinor bivectors?
Okay, so given the directional dependence of Finsler geometry, the Y part again, spinor fields in this framework have to be constructed as sections of a coherence-modulated spinor bundle. That's technical jargon, but it essentially means they don't just carry positional information, where they are X.
They also know which way they're pointing.
Exactly. They also carry crucial directional dependence.
Yeah.
How they're oriented or moving within the anisotropic fabric of space. So a spinor field, traditionally just written as X, is now represented as XY, incorporating that directional component explicitly.
Okay. And how they evolve.
Their evolution is then governed by a Finsler covariant derivative. This modified derivative is key because it replaces the traditional spin connection, which accounts for how spinors change in curved spacetime, with one that is generalized for the Finsler manifold.
Generalized how?
Crucially, it's now modulated by the local coherence structure, rather than simply being fixed by metric curvature alone. This means the way spinors change and propagate is intimately tied to the local coherence properties of the space around them, the local twists and flows and asymmetries. They adapt dynamically.
And the gamma matrices, they're fundamental to the traditional Dirac equation, the equation that describes electrons and other spin-12 particles. Do they change too?
Yes, they get a significant upgrade here. In conventional quantum field theory, the gamma matrices, usually written Ga, are fixed algebraic symbols, constants essentially. Here, they are replaced by directional gamma structures, X.
So they're not constant anymore.
No longer static at all. They dynamically adapt to local coherence conditions, varying with both position X and direction Y. Their mathematical definition, K-Pa-Ku, shows their direct dependence on the Finsler metric tensor Gi XY, which itself depends on X and Y.
So the rules encoded by the gammas change with location and direction.
Exactly. This dynamic adaptation allows spinor dynamics to precisely reflect direction-dependent coherence gradients, directly influencing field behavior and the expression of chirality. It's a much more flexible and responsive mathematical description of how spin manifests in a universe where the underlying coherence is constantly evolving and directionally structured.
So we're building up to a completely new kind of equation for these reimagined spinors. This must be the hyperchiral spinor equation mentioned in the paper.
Indeed. The generalized Dirac-like equation in this framework is presented as IXY d plus XXY plus MXY equals 0.
Okay, let's try to break that down. It looks like the Dirac equation, but different.
It has familiar parts, but with crucial modifications. The dx are those dynamic directional gamma structures we just talked about, acting as the directional resonance operator. The d is the Finsler covariant derivative, including the coherence-modulated spin connection.
What about the EG term? That usually represents electromagnetic fields.
Here, MXY represents a more general, coherence-coupled gauge field. So yes, it includes electromagnetism, but potentially other forces too, all intrinsically linked to the underlying coherence dynamics and potentially direction-dependent.
And the MXY, that's mass.
Yes, but critically, MXY is the mass function, which very significantly arises directly from coherent symmetry reduction. It's not a fixed input parameter like in the standard model. It's a dynamic function of position and direction determined by how coherence is breaking down locally.
Wow. So what does this all mean for how we understand particles? What does this equation tell us about the behavior of fundamental entities in this universe of coherence?
Fundamentally, this equation governs how those resonance bifurcations, those splitting or twisting events in the coherence field, propagate through the Finsler manifold as spinor fields. It dynamically adjusts their behavior based on local coherence conditions, the curvature of the manifold, and its anisotropy, its directional structure.
So it connects everything.
It really aims to. It attempts to restore spinors to their ontological origin as localized symmetry reductions within the universal coherence field, rather than just treating them as abstract algebraic objects we plug into equations.
Yeah.
It's intended as a unified generative model for chirality, for spin, and for directionally emergent matter, directly linking them all back to the fundamental coherence of the universe and its dynamic, direction-dependent geometry described by Finsler space.
It's a truly elegant framework trying to explain rather than just describe the origins of these fundamental properties.
That's the goal, yes. Explanation over description.
That's a huge shift in perspective, moving from a static view of properties to a dynamic, emergent one. Now, to truly understand how all these pieces fit together and how such a system would evolve, we need to formalize the dynamics. That brings us to part 5, the dynamics of coherence, Lagrangian, and field equations.
Right, getting into the engine room.
For those less familiar, a Lagrangian is, well, it's like a blueprint, isn't it? A mathematical recipe for how a system behaves, how it evolves over time.
That's an excellent way to think of it. In physics, the Lagrangian essentially defines the action of a system, a quantity related to energy and time. And physical systems tend to evolve in a way that minimizes this action, following the path of least resistance, or more accurately, the path of stationary action.
The principle of least action.
Exactly. This particular Lagrangian described in the paper is meticulously designed to fully incorporate the directional dependence of coherence modulation, that bivectorial nature of emergent spinors we discussed, and the tensorial structure of hyperchirality.
So it has all those new ingredients baked in.
Right. It's the underlying mathematical principle intended to govern how these resonance bifurcations evolve, interact, and ultimately generate all the physical observables we detect across what the paper describes as the layered hyperspace manifold. The paper defines the overall coherence field action, S, as the integral of a Lagrangian density, L, over spacetime, and that Lagrangian density is made up of 3 foundational components.
3 parts. What are they?
They essentially sum up the system's kinetic energy, its interaction energy, and its mass energy, but defined in this new coherence context. So you have Leakin, Lint, and L mass.
Okay, let's start with the kinetic term, a Lunkin. What does that represent in this coherence-driven universe? What's it describing?
The kinetic term, which has a specific mathematical form involving the spinor field A and the derivative day, describes the resonance flow of spinor fields through this anisotropic coherence manifold. Remember, we discussed how the gamma structures, AXY, are directionally adaptive, derived from the Finsler metric.
And the derivative day includes the coherence effects.
Precisely. So this kinetic term isn't just about simple motion like MVAR. It embodies how these coherent split field modes are reimagined spinors propagate and evolve within a directionally structured field space, dynamically aligning themselves with the local coherence gradients. It's a picture of particles not just moving in space, but moving through a space whose very properties are changing with direction and flow, influencing their movement.
Then there's the interaction term, lint. What does that tell us about how these fields engage with each other? How do forces arise?
The interaction term, again with its own specific mathematical form, involving A, and A, describes the coupling between the hyperchiral spinor fields and coherence-induced gauge fields, those A fields we mentioned.
The force fields.
Right. These gauge fields are the fundamental forces in this framework, and they themselves are seen as intrinsically arising from coherence dynamics. Now, crucially, the coupling coefficient, usually denoted G or similar, representing the strength of the interaction.
Like the electric charge E.
Exactly. That coupling strength isn't necessarily a fixed constant in this theory. It's potentially a directionally variable coupling coefficient, Gxy, meaning the strengths of the interaction could actually change depending on the direction of coherence flow or the local resonance conditions.
The force gets stronger or weaker depending on direction.
Potentially, yes. This allows for what the paper calls phase-specific coupling effects, such as resonance alignment, where fields might reinforce each other more strongly along certain pathways, or decoherence damping, where interactions might weaken coherence along others. This term signifies how hyperchiral fields don't just exist in isolation. They actively entrain with local coherence flows, and these resonance asymmetries give rise to force-like interactions. It effectively tries to unify coherence dynamics with fundamental forces.
And then, perhaps the most critical term for many of us, conceptually at least, is the mass term, L mass. Because in this framework, mass isn't fundamental. It's not simply an inherent property particles just have, right?
That's arguably one of the most revolutionary and, I think, elegant aspects of this theory. In this framework, mass is fundamentally not a fundamental quantity but a measure of coherence loss, the reduction of symmetry and restoration capacity in a localized field region.
A measure of coherence loss.
Yes. So if we connect this to the bigger picture, mass, in this framework, isn't something intrinsic to a particle. It's a symptom, a measurable consequence of coherence disappearing or reducing its symmetry in a localized field region. The mass term is written with that dynamic mass function, mxy.
And where does that mxy come from?
It's described as being locally emergent, arising directly from the directional gradient of the coherence tensor field itself. It quantifies how rapidly coherence symmetry collapses along a specific directional phase pathway. This directly embeds mass energy equivalence, since mass is related to this coherence gradient energy within the dynamic coherence structure itself, rather than needing an external mechanism like the Higgs field to give particles mass. Mass is the signature of broken coherence.
So by combining these three components in the Lagrangian kinetic interaction and mass and applying the principle of least action, we arrive at the derived hyperchiral field equations. What's the big takeaway from these equations for physicists and, well, anyone trying to understand the universe?
By mathematically varying the action derived from this Lagrangian, which is a standard technique in physics, we derive the central hyperchiral Dirac-type dynamics equation we saw earlier. I xy d plus 0.
The main equation of motion.
Exactly. This equation essentially governs how coherence-derived spinor modes evolve and interact within a curved anisotropic Finsler space. It represents a profound generalization of the conventional Dirac equation, which, as you know, is absolutely foundational to quantum mechanics for describing electrons and other fermions.
How is it generalized?
By embedding it within the full coherence tensor field dynamics. This framework shows that chirality, mass, and spin are no longer external inputs or fixed properties you have to plug into the equation. Instead, they emerge naturally and dynamically from the geometric modulation via I and do and symmetry reduction via M and A of the underlying coherence field. This single equation aims to provide a unified mathematical language for describing a universe where properties arise from dynamic field interactions, rather than being simply assigned as labels.
And the solutions to this equation, you mentioned they reveal a resonance quantization spectrum where discrete field types emerge from coherence modulation. So it's not just a continuous flow, but specific emergent states, almost like steps on a ladder, or specific frequencies.
Exactly, like specific resonant frequencies or stable patterns. The solutions demonstrate that specific discrete field types emerge from the way coherence is modulated and reduced. This isn't just a mathematical quirk. It leads directly to what the paper calls a symmetry cascade model.
A symmetry cascade.
Think of it as different zones or thresholds of coherence loss leading to distinct physical outcomes. In zones of high coherence preservation, where symmetry is largely intact, you find massless symmetric fields behaving much like photons.
Okay, maximum coherence massless particles.
Right. Then in areas of partial coherence loss, where some asymmetry or torsion appears, you get chiral fields with fractional mass, which could potentially explain particles like neutrinos with their tiny masses and oscillations.
Partial coherence loss, small mass, chirality.
And finally, in zones of significant decoherence or symmetry reduction, where the coherence is strongly broken directionally, you find massive asymmetrical particles, like electrons and quarks, the building blocks of matter as we know it. It's envisioned as a beautiful cascade where all the diverse structures and properties we observe in our universe arise directly from the progressive reduction of an underlying coherence symmetry.
This is truly a unified picture, and it even affects how we understand fundamental geometric concepts like curvature, torsion, and tensorial chirality in coherence fields. They aren't just background geometry anymore.
No, not at all. In traditional differential geometry, curvature describes how space bends, and torsion describes how it twists, usually treated as properties of the spacetime manifold itself. But within the HHH-CR-TOE framework, these geometric features acquire a much deeper ontological meaning.
Ontological again, about the nature of being.
Yes. They don't just describe geometry. They are seen to reflect phase asymmetries in the coherence tensor field. In other words, they are structured breakdowns of omnidirectional resonance. They are the tangible geometric manifestations of the coherence field losing its perfect uniform symmetry in specific ways.
So Finsler curvature isn't just geometric bending, it's a sign of coherence torsion gradient or something more profound.
Obviously. The Finsler curvature tensor, R-Jack-Hiley in this context, is interpreted as quantifying coherence divergence. If there's zero curvature, it means you have perfect omnidirectional coherence invariance, that state of pure, undisturbed symmetry.
Flat coherent.
Kind of, yeah. But if there's non-zero curvature, it signals phase twisting or coherence anisotropy, directly revealing the presence of structured asymmetry, which is the very essence of hyperchirality. So field curvature becomes a kind of tensorial shadow of coherence torsion. It reflects the rotational phase imbalance within the underlying coherence field. It's not just a bend in space, it's a manifestation of a fundamental twist in the coherence that creates the perceived bend.
And torsion itself, the twist, is described as irreducible coherence twist. That implies a kind of permanent directional memory, doesn't it? Something that doesn't just smooth out.
Yes, there's a very apt description.
Mm-hmm.
Torsion, Keiski, in Finsler space, is interpreted as directly expressing the irreversibility of resonance bifurcation in hyperchiral regions. When coherence collapses directionally, for instance, during phase transitions, or the emergence of mass torsion becomes a non-zero persistent feature of the manifold structure.
It leaves a mark.
Exactly. This indicates a topological twist in the resonance field, a directional memory of the coherence asymmetry that cannot be undone easily. It also marks the structural emergence of spinor orientation, mass, or parity-breaking behavior. It's seen as a primary resonance condition, defining the chirality and rotational asymmetry of emergent fields, essentially imprinting a handedness or twist that persists in that region of space.
And finally, we get tensorial chirality from curvature-torsion coupling. This is where it all truly connects, the geometry and the coherence asymmetry, right?
This is indeed where the profound synthesis occurs. The hyperchiral tensor field, CHICI, which the paper defines with a specific mathematical form that explicitly links components of the curvature tensor and the torsion tensor T.
So it combines bending and twisting.
Yes, it's introduced as directly representing quantized directional asymmetry. This tensor explicitly links geometric asymmetry, the bending and twisting of the Finsler manifold, to the underlying coherence modulation. The existence of a non-zero hyperchiral tensor indicates a zone of resonant chirality emergence, a hyperfractal region, where directionally coherent structures differentiate into observable field states with specific handedness.
So the geometry is the asymmetry.
It truly shows how the geometry of spacetime itself is envisioned as a dynamic mirror of the coherence field's internal symmetry or asymmetry, making chirality an intrinsic geometric part of the universe's dynamic evolution, not just a particle property.
This truly sounds like a complete overhaul of our fundamental understanding of physics and the cosmos. Which brings us, I think, logically to part 6, grand applications reshaping physics and cosmology.
Right, where the rubber meets the road, cosmically speaking.
This is where we see the truly profound implications of this HHH-CR-TOE framework play out. Let's start with one of the most fundamental properties of matter: mass generation, beyond the Higgs field.
This is definitely one of those exciting conceptual shifts proposed. In the standard model, as most people know, mass is primarily explained by the Higgs mechanism. Particles acquire mass by interacting with a ubiquitous Higgs field that permeates space.
The more they interact, the more massive they are.
Roughly speaking, yes.
Yeah.
But what's fascinating here is how this HHH-CR-TOE model completely reinterprets mass. As we discussed with the Lagrangian, it proposes that mass emerges directly from directional coherence asymmetry as a measure of local coherence gradient tension.
Tension in the coherence field.
Exactly. It's not a coupling to an external scalar field like the Higgs. It's presented as an intrinsic property of the coherence field's own dynamic evolution, a direct consequence of its loss of perfect symmetry in a given region.
So what are the implications of mass not being fundamental, not inherent, but rather something emergent from coherence? How does this change our understanding of different particles we observe?
Well, it implies several potentially groundbreaking things. For example, regions of full undisturbed coherence, where symmetry is perfectly preserved, like maybe where photons exist, would naturally remain massless, which aligns with observation.
Photons have zero mass. Checks out.
Conversely, massive fields, such as those that constitute fermions like electrons and quarks, would appear precisely in zones where significant directional decoherence occurs, where that symmetry is strongly broken.
Okay, broken coherence, more mass.
Right. And perhaps most elegantly, phenomena like mass oscillation, which is famously observed in neutrinos, where they seem to change their flavor, electron, muon, tau, as they travel, hinting at incredibly tiny, non-zero masses.
The neutrino puzzle.
This oscillation could potentially rise naturally from dynamic coherence gradients within this framework. As neutrinos travel through varying coherence environments, their effective mass, related to the local coherence loss, could fluctuate, causing the oscillations.
So you wouldn't need to just arbitrarily assign them tiny masses.
Potentially not. This could explain neutrino behavior without needing explicitly assigned small mass terms in the Lagrangian, offering a potentially much more unified and elegant explanation for something we observe directly. It implies that mass is a local fingerprint of the universe's energetic flow and its dynamic reduction in perfect order.
And this framework even offers a new perspective on one of the biggest, most enduring mysteries in cosmology. Dark matter as coherence condensates. I mean, our current models estimate dark matter makes up, what, about 27% of the universe's mass energy?
Something like that, yeah.
A huge chunk.
But we haven't directly detected it, despite looking for decades. That's right. The conventional approach to dark matter is generally to postulate some kind of undiscovered, weakly interacting massive particle, often called a WIMP, or maybe an axion, that we simply haven't managed to find yet.
Still searching.
But what's fascinating here is how this HHACR-TOE model addresses dark matter completely differently. Instead of an undiscovered particle, it proposes dark matter could be understood as a hyperchiral coherence condensate.
Coherence condensate, what's that?
Imagine pockets or regions of the universal coherence field that have partially decohered, meaning they've lost some of their initial perfect order, they've gained some structure, but critically, they remain as non-interacting resonance modes.
Non-interacting meaning.
Meaning they're not strongly coupled to the familiar particles and forces of the standard model, electromagnetism, strong and weak forces, which beautifully explains why we can't detect them through conventional means, like light or direct particle collisions.
Ah, so that explains the dark part.
Exactly. Yet these condensates would retain structured resonance patterns within the overall Finsler manifold, and crucially, they would still exhibit gravitational effects via curvature-torsion coupling.
So they still have gravity?
Yes, because they represent a region of altered coherence, which in this model is the source of gravitational effects, curvature and torsion. They affect space-time geometry, but not through the direct energy-momentum tensor sourcing like normal matter. So dark matter could simply be the structured, asymmetric, but non-interacting residue of this universal coherence, structuring the universe gravitationally without being made of stuff as we normally understand it.
A completely different ontological picture indeed. Not particles, but structured coherence patterns.
It's a radical alternative for sure.
And this touches on another huge cosmological puzzle, cosmic chirality and matter-antimatter asymmetry. We live in a universe almost entirely made of matter, with hardly any antimatter floating around. Which is weird because the Big Bang model, in its simplest form, predicts equal amounts of both should have been created.
The universe's observed matter-antimatter imbalance, or baryon asymmetry, is indeed a huge unresolved problem for conventional physics and cosmology. Many theories propose new particles or new kinds of interactions, like CP violation, to explain it, often requiring quite specific conditions in the early universe.
Right, finding that mechanism is key.
This coherence framework offers a potentially refreshingly elegant solution. It attributes the imbalance to a cosmic-scale hyperchirality bias that might have been present at the very moment of cosmological emergence.
A built-in handedness to the universe from the start.
Essentially, yes. If you recall, hyperchirality is the fundamental directional asymmetry of the coherence field. If there was an initial fundamental bias in this hyperchirality right at the beginning,
How would that help?
this initial bias would skew early universe coherence bifurcations towards certain spinor modes. Remember the symmetry cascade. It would lead to matter-preferred coherence trajectories, naturally suppressing antimatter emergence. It's presented as a possible intrinsic mechanism for baryogenesis, the creation of baryonic matter, that doesn't necessarily require exotic, unproven, CP-violating terms added onto the standard model. It proposes that the universe, right from its deepest origins in the coherence field, had a preferred handedness, a hyperchiral bias, leading naturally to a matter-dominated cosmos.
So the dice were loaded from the start by the coherence field itself.
That's the idea.
And if gravity isn't caused by mass energy in the direct way Einstein described in general relativity, what is the gravitational field as emergent coherence curvature in this model? How does gravity actually work here?
Okay, so in general relativity, gravity is fundamentally understood as space-time curvature caused by the presence of mass and energy. Massive objects warp the fabric of space-time, and that warping dictates how other objects move. That's what we experience as gravity.
Geometry is gravity.
Right. Here, within the HHH-CR gravity is reinterpreted. It's seen as a structured projection of the coherence tensor curvature. This means the coherence field's intrinsic curvature, its very bends and twists described by the Finsler geometry, is what directly determines the emergent gravitational signature we observe.
So coherence curvature is gravity.
Essentially, yes.
Yeah.
Mass energy, in this view, becomes a secondary effect of coherence symmetry loss, not the primary source of curvature. The coherence breakdown causes both mass and gravity, curvature torsion, rather than mass causing gravity.
That's a fundamental reversal.
It is. Furthermore, torsion-dominated regions, such as the extreme environments predicted near or inside black holes, are described not as geometric singularities in the traditional sense, where space-time curvature becomes infinite and physics breaks down,
The singularity problem.
but rather as zones of hyperchiral collapse, where directional coherence symmetry is utterly destroyed. Imagine coherence becoming completely scrambled and twisted. This could potentially resolve many paradoxes associated with singularities and information conservation in black holes by seeing them as extreme states of coherence redistribution and maximal asymmetry rather than points of infinite density or geometric infinities.
A different kind of extreme state, not an infinity.
Exactly.
A state of maximal coherence, torsion, perhaps.
So, think about the very beginning. The early universe wasn't simply a hot, dense Big Bang as we typically envision it,
The initial fireball idea.
but rather a coherence phase emergence, almost like an unfolding from a deeper, more ordered state.
Yes, that's the picture this model paints. Instead of an initial hot, dense Big Bang singularity expanding outwards, this model suggests the early universe emerged from a coherence cascade, a multi-stage sequential reduction of that primordial homoelectric field into progressively more structured, directionally structured manifolds.
A cascade, like steps down. Right. Finsler geometry, with its capacity for directional sensitivity, becomes the first projection scaffold for dimensional layering, allowing dimensions to literally unfold or emerge from the coherence field. Hyperchirality, being the very first breakdown of isotropy, uniformity in all directions, effectively signals the initial differentiation. It seeds dimensionality itself, leads to things like charge separation, and even establishes the fundamental arrow of time through irreversibility of coherence loss.
Wow, even the arrow of time comes from this.
Potentially, yes, linked to the irreversible nature of symmetry breaking and torsion. This model completely replaces traditional thermal phase transitions in the early universe, where properties change based on temperature cooling down with resonance bifurcation thresholds. New phases of reality emerge as the coherence field crosses certain symmetry thresholds, as its eigenvalue spectrum changes.
So it's driven by coherent structure, not temperature.
Exactly. It's a universe being born not from a chaotic explosion, but from an ordered unfolding, a cascade of coherence breaking symmetry and generating complexity and structure as it goes.
This all sounds incredibly theoretical, almost abstract in its grandeur, which naturally raises an important question. How on earth do we test these profound ideas? What are the experimental probes and predictions that could actually validate, or just as importantly, falsify this HHHCR-TOE framework?
That's the critical question for any scientific theory, isn't it? If you can't test it, it remains philosophy. While the coherence effects are predicted to be subtle, perhaps hidden beneath standard physics effects, the model does predict specific observable consequences that would require subtle yet incredibly precise measurements.
Like what, for example?
Well, one example highlighted is in neutrino oscillation phase anomalies. Neutrinos, as we know, oscillate between different flavors, electron, muon, tau, as they travel vast distances. This model predicts there could be direction and curvature-dependent shifts in oscillation phase.
So how they oscillate depends on where they're going and the geometry they pass through.
Exactly. This means that long baseline neutrino experiments, like those sending beams through the Earth, especially if they traverse varying gravitational gradients or regions of potential coherence torsion, maybe deep within the Earth, could potentially reveal these tiny coherence-induced phase delays or damping patterns that wouldn't be explained by the standard model alone with just neutrino masses.
Interesting. What about experiments here on Earth, perhaps in high-field environments that we can actually manipulate and control?
Absolutely. Another avenue is looking for spinor decoherence in high-field environments. Experiments involving spinor matter, like electrons or muons placed in very strong magnetic fields, or perhaps torsion-prone conditions.
Like what?
For instance, near rapidly rotating superconductors, which might generate exotic spacetime effects, or even simulating environments astrophysically found near neutron stars. These experiments might show evidence of what the paper calls non-inertial coherence divergence, meaning the spin behavior, how the particle's spin precesses or decoheres, might deviate from conventional predictions in ways that align specifically with the Hyperchirality's predictions about coherence interaction. Another really promising area is gravitational coercion probes using atom interferometry.
Atom interferometry. That sounds sensitive.
Incredibly sensitive. These instruments use the quantum wave nature of atoms to measure tiny variations in gravity or acceleration. Highly precise setups could, in principle, detect subtle decoherence signatures or phase shifts that betray the presence of localized torsion fields, those twists in coherence effects that go beyond what standard general relativity alone predicts.
And even the vacuum itself, the seemingly empty space around us, could hold clues. You mentioned that earlier.
Yes, absolutely. The Finsler modulated coherence field implies anisotropic vacuum resonance effects. This means that the vacuum's refractive index, how light behaves as it travels through supposedly empty space, might subtly change depending on the direction of propagation relative to some underlying coherence flow or gradient.
So light travels slightly differently north versus east.
Potentially on an incredibly minute scale. Extremely sensitive laser interferometry, maybe building on LIGO-like technology, or cavity QED, quantum electrodynamics systems trapping light, could be designed to look for these minute directional phase distortions or frequency shifts in vacuum. Such distortions would be direct signatures of underlying coherence gradient flows, offering a unique window into the dynamic directional nature of the vacuum predicted by this theory.
So there are potential tests, even if they're incredibly difficult.
Difficult, yes, but perhaps not impossible with advancing technology. These experimental avenues are crucial for moving the HHHCR TOE from being a purely theoretical model to becoming an empirically testable framework, inviting verification or, equally importantly, refutation.
Beyond direct experiments, how do we even begin to model and simulate this incredibly complex dynamic reality? We'd clearly need new computational models of coherence tensor fields. You couldn't just use existing physics simulators.
Indeed, this represents a massive computational challenge, absolutely. The next crucial step, alongside experimental efforts, would be building dynamic simulations of the coherence tensor field Casway itself. These simulations would need to include how its curvature, torsion, and hyperchiral components evolve over time and across different regions of the Finsler manifold.
What would these simulations show us?
Ideally, they would allow us to visualize field bifurcations and mass emergence thresholds. We could essentially map the geometry of these symmetry reduction cascades in action. Imagine being able to see, in a computer simulation, how a perfectly coherent field begins to twist and turn, how hyperchirality develops, leading to the emergence of structures that we recognize as mass or spin.
Like watching particles form from the field.
Exactly. We could potentially manipulate the coherence phase space parameters in real time within these simulations to observe how emergent field dynamics unfold under different conditions. This would be invaluable for guiding future experiments, generating new specific predictions, and really understanding the theory's vast implications in a more tangible, visual way.
And this takes us to an even wilder frontier mentioned in the paper, activating higher dimensional coherence layers. This suggests that dimensions aren't just fixed properties of the universe, but might be dynamic and even influenced. That sounds like science fiction.
It does stray into highly speculative territory, but it's a logical, if profound, prediction arising from the framework's core ideas. Yes, the HHHCR TOE explicitly predicts that dimensionality isn't necessarily fixed, but unfolds through coherence reduction. Finsler geometry, as we discussed, provides the mathematical structure needed to express active directional coherence, possibly operating in these higher dimensions.
So how would we even think about that?
Future theoretical work could involve trying to define coherence embedding functions across nested dimensional shells. Imagine a series of nested mathematical layers, like Russian dolls, where each higher layer, M4 plus N, introduces new coherence axes, new directions for symmetry breaking, and potentially entirely new field behaviors.
Unlocking higher dimensions through coherence.
Perhaps. We could also explore projection thresholds, which would be the minimum coherence symmetries or resonance conditions required for a dimensional layer to stably project its influences down into lower dimensional manifolds, like our familiar 4D spacetime. This truly opens a pathway toward hyperfractal coherence activation, which, yes, could potentially enable new forms of matter, new interactions, or even, as the paper speculates, coherence propulsion technologies.
Propulsion by manipulating coherence. Wow.
It's definitely where cutting-edge theoretical physics starts to brush against what was once purely the domain of science fiction. But the mathematical framework at least allows for these possibilities.
And this model isn't just for theoretical physicists pondering the cosmos. It has incredibly broad implications suggested for integration with coherence technologies and intelligent systems across various fields, even AI.
Precisely. This hyperchiral coherence framework, if validated, could have direct intersections with applied and emerging technologies, far beyond just fundamental physics. For instance, in quantum coherence devices.
Quantum computers and sensors.
Right. This model could provide an entirely new theoretical underpinning, guiding the design of next-generation quantum systems that intentionally exploit or stabilize coherence asymmetry, perhaps leading to more robust quantum computing architectures or highly sensitive quantum sensors that leverage these directional effects.
What about coherence engines?
That's even more speculative. But imagine devices that could actively manipulate or reproject coherent symmetry based on these Finsler resonance principles. Maybe they could be used to correct decoherence in quantum systems far more effectively, or perhaps even generate directed coherence thrusts for propulsion, as mentioned before.
And AI, how does coherence connect to AI?
The paper suggests that intelligent AI systems, which could be thought of as highly integrated, perhaps globally distributed multi-agent networks, might actually model their internal dynamics using coherence tensor frameworks. This could allow for recursive self-organization around optimized resonance states, leading to truly emergent intelligence that learns and adapts based on maintaining or evolving its internal coherent structure.
AI based on coherence principles.
It's a fascinating thought. This model thus becomes potentially more than just a theory of fundamental physics. It offers a potentially universal structuring principle applicable to advanced technology, communication, computation, and maybe even cognition itself.
This is truly expansive, connecting the most abstract ideas in theoretical physics to potential real-world applications and even the nature of intelligence. And finally, it circles back to the biggest questions of all, the philosophical and ontological continuation.
Where science meets meaning.
So what does this all mean for us, the listeners, and our fundamental understanding of existence itself? Where does this leave us?
Well, these inquiries truly complete the deep dive, don't they? They invite a shift in perspective beyond the purely scientific equations and predictions. The framework really compels us to ask some provocative questions like, what is the true origin of chirality in a reality structured by resonance?
If it's not just particle property.
Right. If everything is this dynamic dance of coherence twisting and untwisting, then even something as fundamental as the handedness of nature takes on a new, deeper meaning. Perhaps it hints at a fundamental bias or choice within reality itself right from the beginning.
And consciousness, you mentioned that earlier too.
Yes, another profound question posed is, can consciousness itself be understood as a coherence-preserving meta-observer? This is a truly radical thought, suggesting that consciousness isn't just an emergent property of complex brain chemistry.
The standard view.
But could potentially be a fundamental aspect of reality, intrinsically linked to the coherence field, perhaps even actively working to preserve it, organize it, or experience its bifurcations. It opens up entirely new avenues for thinking about the mind-body problem.
And what about the implications for our understanding of morality, maybe, or even just the very act of existing and interacting with the world around us?
Yes, the framework prompts us to consider what are the ethical and epistemological consequences of living in a universe where all emergence is directional coherence loss.
Emergence as loss? That sounds negative.
Or maybe just change. If everything we perceive as real, every particle, every structure, every dimension comes into being through a process of coherence reduction, of perfect symmetry breaking into complexity, How does that change our perception of creation, destruction, and even our own place within this cosmic unfolding?
If our existence is a loss of a deeper unity.
What does that imply about our ultimate connection to the universe? Or perhaps our yearning for unity or meaning? These inquiries, as the paper suggests, complete it by restoring coherence to its proper place, as both the generator of structure and the ground of being. It shifts our potential understanding from a purely material-first universe to perhaps a coherence-first universe, where being and becoming are intrinsically linked through these dynamic processes of symmetry breaking and resonance.
We've taken a really deep dive today into a truly revolutionary vision of physics, where hyperchirality, Finsler geometry, and the HHHCR toe invite us to see mass, spin, and even gravity not as fixed, isolated properties,
Not as static labels.
but as dynamic signatures, as emergent phenomena arising from a universal coherence field.
It's a profound shift, definitely,
Hmm.
suggesting that hyperchirality, that fundamental asymmetry, is truly the signature of becoming. It's the torsional inflection point where pure, undifferentiated coherence begins to fracture, curve, twist, and sing into form, giving rise to all the complexity and asymmetry we observe in our universe.
So here's a final thought to leave you with. Consider this. If everything in our universe, every particle, every force, every dimension we experience is simply a manifestation of coherence, twisting and untwisting along directional paths, what does that say about the ultimate unity and interconnectedness of reality?
Does it imply deeper resonance underlying everything?
It certainly challenges us to look beyond the surface of what we perceive as separate and discrete and perhaps contemplate a deeper, more resonant truth about existence itself, a universe woven from coherence.
We definitely invite you to continue pondering these deep questions long after this deep dive is over. The age of coherence, if this theory holds any water, might just be beginning, and there's clearly so much more to explore within this fascinating, potentially paradigm-shifting framework.